PostgreSQL, often simply Postgres, is an object relational database management system with an emphasis on extensibility and standards compliance. As a database server, its primary function is to store data securely, supporting best practices, and to allow for retrieval at the request of other software applications. It can handle workloads ranging from small single-machine applications to large Internet-facing applications with many concurrent users. PostgreSQL implements the majority of the SQL 2011 standard, is ACID-compliant and transactional, avoiding locking issues using multi-version concurrency control, provides immunity to dirty reads and full serializability, handles complex SQL queries using many indexing methods that are not available in other databases, has updatable views and materialized views, triggers, foreign keys, supports functions and stored procedures, and other expandability, and has a large number of extensions written by third parties. In addition to the possibility of working with the major proprietary and open-source databases, PostgreSQL supports migration from them. By its extensive standard SQL support and available migration tools, proprietary extensions in databases such as Oracle can be emulated by built-in and third-party open-source compatibility extensions. Recent versions also provide replication of the database itself for availability and scalability. PostgreSQL is cross-platform and runs on many operating systems including Linux, FreeBSD, OS X, Solaris, and Microsoft Windows. On OS X, PostgreSQL has been the default database starting with Mac OS by 10.7 Lion Server, and PostgreSQL client tools are bundled within the desktop edition. The vast majority of Linux distributions have it available in supplied packages. PostgreSQL is developed by the PostgreSQL Global Development Group, a diverse group of many companies and individual contributors. It is free and open-source software, released under the terms of the PostgreSQL license, a permissive free software license. Name: PostgreSQL's developers pronounce it PostgreSQL. It is abbreviated as Postgres, its original name. Because of ubiquitous support for the SQL standard among most relational databases, the community considered changing the name back to Postgres. However, the PostgreSQL core team announced in 2007 that the product would continue to use the name PostgreSQL. The name refers to the project's origins as a post-Angra database, being a development from University Angra DBMS. History: PostgreSQL evolved from the Angra project at the University of California, Berkeley. In 1982, the leader of the Angra team, Michael Stonebreaker, left Berkeley to make a proprietary version of Angra. He returned to Berkeley in 1985, and started a post-Angra project to address the problems with contemporary database systems that had become increasingly clear during the early 1980s. The new project, Postgres, aimed to add the fewest features needed to completely support types. These features included the ability to define types and to fully describe relationships, something used widely before but maintained entirely by the user. In Postgres, the database understood relationships, and could retrieve information in related tables in a natural way using rules. Postgres used many of the ideas of Angra, but not its code. Starting in 1986, the Postgres team published a number of papers describing the basis of the system, and by 1987 had a prototype version shown at the 1988 ACMS IGMODA conference. The team released version 1 to a small number of users in June 1989, then version 2 with a rewritten rules system in June 1990. Version 3, released in 1991, again rewrote the rules system, and added support for multiple storage managers and an improved query engine. By 1993, the great number of users began to overwhelm the project with requests for support and features. After releasing version 4.2 on June 30, 1994, primarily a cleanup, the project ended. Berkeley had released Postgres under an MIT-style license, which enabled other developers to use the code for any use. At the time, Postgres used an Angry-influenced PostgreSQL query language interpreter, which could be interactively used with a console application named Monitor. In 1994, Berkeley graduate students Andrew Yu and Jolly Chen replaced the PostgreSQL query language interpreter with one for the SQL query language, creating Postgres 95. The front-end program Monitor was also replaced by PSQL. Yu and Chen released the code on the web. On July 8, 1996, Mark Fournier at Hub.org Networking Services provided the first non-university development server for the open-source development effort, with the participation of Bruce Momkian and Vadim B. Mikey's work began to stabilize the code inherited from Berkeley. The first open-source version was released on August 1, 1996. In 1996, the project was renamed to PostgreSQL to reflect its support for SQL. The online presence at the website PostgreSQL.org began on October 22, 1996. The first PostgreSQL release formed version 6.0 on January 29, 1997. Since then, a group of developers and volunteers around the world have maintained the software as the PostgreSQL Global Development Group. The PostgreSQL project continues to make major releases and minor bug fix releases, all available under its free and open-source software PostgreSQL license. Code comes from contributions from proprietary vendors, support companies, and open-source programmers at large. See also release history below. Multi-version concurrency control. PostgreSQL manages concurrency through a system known as multi-version concurrency control, which gives each transaction a snapshot of the database, allowing changes to be made without being visible to other transactions until the changes are committed. This largely eliminates the need for read locks, and ensures the database maintains the ACID principles in an efficient manner. PostgreSQL offers three levels of transaction isolation: read committed, repeatable read, and serializable. Because PostgreSQL is immune to dirty reads, requesting a read uncommitted transaction isolation level provides read committed instead. Prior to PostgreSQL 9.1, requesting serializable provided the same isolation level as repeatable read. PostgreSQL 9.1 and later support full serializability via the serializable snapshot isolation technique. Storage and replication. Replication. PostgreSQL, beginning with version 9.0, includes built-in binary replication, based on shipping the changes to replica nodes asynchronously. Version 9.0 also introduced the ability to run read-only queries against these replicated nodes, where earlier versions would only allow that after promoting them to be a new master. This allows splitting read traffic among multiple nodes efficiently. Earlier replication software that allowed similar read scaling normally relied on adding replication triggers to the master, introducing additional load onto it. Beginning from version 9.1, PostgreSQL also includes built-in synchronous replication that ensures that, for each write transaction, The master waits until at least one replica node has written the data to its transaction log. Unlike other database systems, the durability of a transaction can be specified per database, per user, per session, or even per transaction. This can be useful for workloads that do not require such guarantees, and may not be wanted for all data, as it will have some negative effect on performance due to the requirement of the confirmation of the transaction reaching the synchronous standby. There can be a mixture of synchronous and asynchronous standby servers. A list of synchronous standby servers can be specified in the configuration, which determines which servers are candidates for synchronous replication. The first in the list, which is currently connected and actively streaming, is the one that will be used as the current synchronous server. When this fails, it falls to the next in line. Synchronous multi-master replication is currently not included in the PostgreSQL core. PostgreSQL, which is based on PostgreSQL, provides scalable synchronous multi-master replication. Available in version 1.1, is licensed under the same license as PostgreSQL. A similar project is called PostgreSQL and is available under the Mozilla public license. The community has also written some tools to make managing replication clusters easier, such as REPMGR. There are also several asynchronous trigger-based replication packages for PostgreSQL. These remain useful even after introduction of the expanded core capabilities. For situations where binary replication of an entire database cluster is not the appropriate approach. Sloaney I. Londeast, part of SkyTools. Bucado multi-master replication. Symmetricd's multi-master, multi-tier replication. Indexes. PostgreSQL includes built-in support for regular B-tree and hash indexes, and two types of inverted indexes: generalized search trees and generalized inverted indexes. Hash indexes are implemented, but discouraged because they cannot be recovered after a crash or power loss. In addition, user-defined index methods can be created, although this is quite an involved process. Indexes in PostgreSQL also support the following features. Expression indexes can be created with an index of the result of an expression or function, instead of simply the value of a column. Partial indexes, which only index part of a table, can be created by adding a where clause to the end of the createIndex statement. This allows a smaller index to be created. The planner is capable of using multiple indexes together to satisfy complex queries, using temporary in-memory bitmap index operations. As of PostgreSQL 9.1, k-nearest neighbors indexing provides efficient searching of closest values to that specified. Useful to finding similar words, or close objects or locations with geospatial data. This is achieved without exhaustive matching of values. In PostgreSQL 9.2 and above, index-only scans often allow the system to fetch data from indexes without ever having to access the main table. Schemas in PostgreSQL. All objects are held within a schema. Schemas effectively act like namespaces, allowing objects of the same name to coexist in the same database. By default, databases are created with the public schema, but any additional schemas can be added, and the public schema isn't mandatory. Search_path determines the order in which schemas are checked on unqualified objects, which can be configured on a database or role level. The search path by default contains the special schema name of $user, which first looks for a schema named after the connected database user. If such a schema is not found, it then proceeds to the next schema. New objects are created in whichever valid schema is listed first in the search path. Data types. A wide variety of native data types are supported, including Boolean, arbitrary precision numerics, character, binary, date, time, money, enum, bit strings, text search type, Composite, HStore, arrays up to 1 GB in total storage size, geometric primitives, IPv4 and IPv6 addresses, CIDR blocks and MAC addresses, XML supporting XPath queries, UUID, JSON, and a faster binary JSONB. In addition, users can create their own data types which can usually be made fully indexable via PostgreSQL's GIST infrastructure. Examples of these include the Geographic Information System data types from the PostGIS project for PostgreSQL. There is also a data type called a domain, which is the same as any other data type but with optional constraints defined by the creator of that domain. This means any data entered into a column using the domain will have to conform to whichever constraints were defined as part of the domain. Starting with PostgreSQL 9.2, a data type that represents a range of data can be used which are called range types. These can be discrete ranges or continuous ranges. The built-in range types available include ranges of integers, big integers, decimal numbers, timestamps and dates. Custom range types can be created to make new types of ranges available, such as IP address ranges using the INET type as a base, or float ranges using the float data type as a base. Range types support inclusive and exclusive range boundaries using the AND represents all integers starting from and including 4 up to but not including 9. Range types are also compatible with existing operators used to check for overlap, containment, right of etc. User-defined objects. New types of almost all objects inside the database can be created, including casts, conversions, data types, domains, functions, including aggregate functions and window functions, indexes including custom indexes for custom types, operators, procedural languages. Inheritance tables can be set to inherit their characteristics from a parent table. Data in child tables will appear to exist in the parent tables, unless data is selected from the parent table using the only keyword, i.e., select asterisk from only parent underscore table. Adding a column in the parent table will cause that column to appear in the child table. Inheritance can be used to implement table partitioning, using either triggers or rules to direct inserts to the parent table into the proper child tables. As of 2010 update, this feature is not fully supported yet. In particular, table constraints are not currently inheritable. All check constraints and not null constraints on a parent table are automatically inherited by its children. Other types of constraints are not inherited. Inheritance provides a way to map the features of generalization hierarchies depicted in entity relationship diagrams directly into the PostgreSQL database. Other storage features referential integrity constraints including foreign key constraints, column constraints, and row checks. Binary and textual large object storage. Table spaces. For column collation. Online backup. Point-in-time recovery, implemented using write-ahead logging. In-place upgrades with PG_upgrade for less downtime.